meeting is being recorded.
All right, I think we can get going. So thank you everyone for tuning in today. We have Alexander Kearney, who's going to be presenting the unified mathematics of cognition. As usual, we'll have about 40 minutes for the talk, Alex, and then some time for Q&A before Carl will give some feedback. So over to you when you're ready.
Hey, so my name is Alexander Kearney, and I did a thesis in integrated information theory at Oxford University. And when I was there, I sort of developed some ideas around information as maximum-calibre deviations, which I'm here to talk about today. So my basic idea is that for anyone who's interested in understanding the relationship between the free energy principle, integrated information theory, and certain ideas in neurophysics, that understanding information as a deviation from a maximum caliber path ensemble might be of relevance there. So we're going to go through a few things. First is how I've seen MaxCal applied in these theories so far and my understanding of it. Second is sorry, 1 second. Second is talking about motivating the Kinetic Ising model from the IIT-inspired view. Third is extending it to FEP. Then we're going to look at how predictive coding might relate to things. And then finally, we'll look through some experiments. So obviously in neuroscience, we have, in free energy principles specifically, we have Bayesian mechanics. Just to clarify how I often use terminology, I tend to use free energy principle to refer to the unifying framework, active inference to refer to the process theories involving Markov blankets and partially observable Markov decision processes. And then, so I'm not sure if that's, I hope I'm using the terminology correctly, but that's sort of the shorthand I use to differentiate between the two. With regards to MaxCal stuff, there's obviously been a lot of work about the dualism between free energy minimization and constrained entropy maximization in the context of a Markov blanket. And there's also been some work on the dualism of maximum caliber in certain contexts. As far as I'm aware, the G theory is still in development. However, you know, please correct me on that if I'm mistaken. In sort of some other areas, there's a whole bunch of consciousness theories. So to be clear, I understand that FEP isn't primarily a consciousness theory. However, there are theories of consciousness related to it. Within the sort of thermodynamics neuroscience side, since around 1967, 1965 or the 1940s, there have been people who thought that maybe consciousness might be associated with an unstable non-equilibrium state, and that free energy is likely minimized during unconscious states. This is a huge body of work to group together, so I'm definitely not trying to be reductionist here. But there's a, unfortunately the video is not rendering. But basically, you know, self-organized criticality is also proposed to work with, to be related to consciousness. And if the video was rendering, that was supposed to give an intuitive picture as to why. Some interesting work by Friedman and Landsberg shows that in hierarchical modular networks, sort of simple updating from the nodes can lead to dynamics which look like self-organized criticality. So I think there's some interesting potential relationships to explore with predictive coding there. And then finally, on the empirical side, we've got some recent empirical work by many of the team behind this, but also behind the discovery of the perturbational complexity index. And they recently fit a thermodynamic process to neural data and found that violations of the Fluctuation Dissipation Theorem could empirically mark consciousness. Meanwhile, Ishihara and Shimazaki recently came up with a state space kinetic Ising model. And what they found is that this was able to better model the non-equilibrium properties of neural networks, biological neural networks, and also that the coupling-driven entropy was a relevant measure of task performance, also some interesting results around sparse coding. Now for integrated information theory. So I think this is a theory which is probably best understood from its highest level downwards. It centers around the hard problem of consciousness and around Chalmers' proposal that there's an explanatory gap between a bunch of neurons firing and, the sensation of seeing the color blue. And my understanding of IIT, this is just my understanding, is that they suggest that the hard problem of consciousness gets the chain of logical inference mistaken, essentially. They believe, so they're not a solipsist theory, they're not denying the importance of the physical world, but what they are saying is, inspired by Descartes, I think, therefore I am, that consciousness is our one fundamental certainty in life. And technically, by embarking on neuroscience, or just engaging with the physical world at all, we're making an assumption about something which exists outside of ourselves. And then, so, in a sense, an assumption of physicalism is built into the discipline. But more specifically, they suggest that the chain of scientific inference should reflect this chain of logical inference on the sort of philosophical level. So the way they try and solve this is to axiomatize consciousness and then make physical predictions out of the conscious processes. And then from there, a process theory can develop and you lead to this metric phi. There have been a few different iterations of IIT, and phi sometimes, they're not all exactly the same. Most of my work pertains to IIT 3.0 because that was the version which was out when I started it. But there's links to IIT 4.0 as well. So how does it relate to MaxCal? This is actually what my thesis was about. So first we need to understand how information is measured on the fundamental level. Basically, it's about the difference between signal and noise. So A equals 1 you take as a signal, and then you look at the set of futures or the space of futures that it imposes on the immediate future. That's this effect repertoire. The unconstrained effect repertoire is if you make everything uniform random noise and then see what future possibilities emerge. So this is a uniform distribution filtered through a transition probability matrix. On the causal side, you look at the set of pasts which A equals 1 imposes. That's the cause repertoire. And then you randomly perturb with uniform random noise all of the unconstrained past. So how does this relate to MaxCal? Basically, this is supposed to be one conscious moment. This is supposed to be the next conscious moment. So, and it's taken to be a sort of fundamental timescale involved there. Second thing is that IIT, in its iteration then, was actually only explicitly defined on deterministic systems. So my original idea was I wanted to extend it out to non-deterministic systems, but I encountered an issue because, you were maximizing the entropy of every single input node, but what you're also doing is you're maximizing the caliber of the path ensemble from one conscious moment to the next to find the unconstrained neutral baseline. And so I set out to try and find out what IIT's intentions were. In IIT 4.0, they've clarified. However, in IIT 3.0, I wasn't necessarily able to ascertain it on first read. But what I found is that basically IIT does not have a predictive definition of information, and it is tempting to view it that way because you have the unconstrained future, the effect repertoire. These things look like predictions, but they're not. If they were making predictions, then they would start from a place of maximal ignorance at these nodes each time for both the past and the future. On the other hand, they're not necessarily taking so information is on tick in IIT, and they're very clear about this as well. They're also clear about it in IIT 4.0. On the other hand, they're not really taking it's not that the information is moving from one place to another either. They are so they're not taking a kind of a lot of people who view information ontically might think of it as a process that's unfolding over time. And that's not necessarily the approach either. What it is it's an interaction between the state and the structure of the system that exists at a fixed moment in time. So this information is, discretized from this information under IIT. There is a clear notion that information flows forward in time because that is part of the causal structure of the system's rules. But fundamentally, it's this synergy between the signal and the structure that creates this integrated information, or just information at this level. And the argument of IIT, I believe, is that this reflects a fundamental information-based property of the system. Now, IIT has an algorithm. One thing I'll say first. This sort of got me asking, what would IIT look like if it took a path-based approach? And I was just curious, part of maths, which is what I was doing at the time, is you tweak things, you change things, and you see what changes about a theory. So I was studying IIT as a mathematical theory, and I was also aware that there are thermodynamic views of consciousness, and that consciousness occurs in life, which is a thermodynamic process. So I just wanted to see what a dynamical IIT might look like. And to assist with this, we can use the IIT algorithm. So this was formalized by Kleiner and Toll. This is the 3.0 algorithm, but we're only going into the level of defining information here anyway. And most of the differences are with regards to how you aggregate it. So it translates across to IIT 4.0. But basically, you observe the whole system in a state, you calculate the information of each part. What constitutes a part? Say X1 and X2 will constitute a part if they produce more information together than they would separately on their own. Once you have each part and you have their cause-effect structures, you combine them, and then you compute system-level information, and then you cut the system and combine it again, and so forth until you get integrated system information. So we're going to just talk about information and a little bit about mechanism integration because, the fundamental level is of more concern to me, because the higher levels are just composing from the fundamental levels. So how do we apply this to paths? The goal of this, to be clear, is not to model the brain or a conscious system of my mathematical exercise with perfect precision. The goal of this was to stay as close to IIT as possible, but just look at it from a path-based lens. And this is what I came up with. You define a transition network. And it's basically, you think of this transition network as a path over which the conscious moment unfolds. So in this case, unfolding over 2 moments in time. And so what happens? Instead of looking at the maximally disordered signal, you would instead look at the maximally disordered set of paths. So everything, in this single step case ends up being geometrically weighted by its conditional entropy. Or you can think of it as the effective number of paths coming out of it. So you can form an equivalent of constrained repertoires as well, constrained input distributions for the MaxCal ensembles. And I don't have too much time to get into this, but because expected entropy is expected negative log probability, and because expected negative log probability in some sort of toy models can be interpreted as an energy term, in my view at the time, I'm not going to say with strict certainty, but an exploration of could this be interpreted through a energy-based lens? Maybe the structure's energy that survives the transition might be how one thinks of information. Now, finally, in terms of looking at the information as a difference between the unconstrained and the constrained, this is where I had to think really hard, because on the one hand, I could try and replicate the specific metric IIT used, which at the time was Wasserstein distance between the outputs, the inputs, or I could sort of try and stay true to what would this look like from a dynamical point of view. I wanted to inject as few of my own assumptions as possible. So that, combined with the intuition that MaxCal over paths represents neutrality, whereas something happening might represent some sort of departure from that, I decided to just use the pure difference as the metric for information. Now, a couple of things. I do understand that this would not represent the long-term MaxCal ensemble of the path. I would like to make that very clear. The mathematics of IIT reflects the perspective that the system in the state is its own, it's experiencing itself from its own perspective. So we're taking the view here that even if over the long run, or we're entertaining the view here that even if over the long run, it tends towards some stationary distribution, in this moment-to-moment setting, it might, just generate an experience that lasts over that moment. And sort of experiences itself in relation to that moment. And then the second thing is that, I like to call this IIT inspired. There are differences to how IIT looks at information. So on the one hand, I don't want to downplay the similarities. The entire mathematical procedure I constructed is isomorphic in the category theory sense to IIT up to this point, which impacts computation. If you want a computation that reflects the, some of the logic of intrinsic information, then you would probably be putting something on to what's already here. Okay, so a few things before I move on. The principle of Maximum-Calibre is going to appear in anything thermodynamic. There are some links with FEP. I'm aware I didn't go into it too much. I assumed I didn't need to for this audience. And then we've also got this MaxCal idea I've sort of constructed in relation to IIT. These are all pretty different theories. That being said, I don't think that they're mutually exclusive. One way you could think about it is you could think of active inference or predictive coding as describing something about the dynamics or about the what the dynamics look like from a Bayesian point of view. You can maybe, as things go up to the top of the cortical hierarchy and become increasingly complex, dynamically and information theoretically, there's room to think of the signals that arise at the top as in complex information-based terms and complex dynamic terms. And so I think there's actually a place where all of these can meet. The other thing is that much sensory signal that comes to us arrives in waves, and it causes disturbances in our nervous system, which are then filtered out, or attempted to be filtered out. And it's the ones which aren't filtered out which, reach the top of our cortical hierarchies. I know I'm speaking very loosely here, so please don't take that too precisely. But I think what I'm saying is that I think there's room to explore each of these theories from the other's point of view, even though they start from profoundly different starting places. So obviously with the formulation I came up with for IIT, we've got a bit of a problem, which is that information probably doesn't exist moment to moment over a Markov chain. And so just to touch on how IIT thinks of this, in IIT 4.0, they suggest that the causes which exist at a higher level could be Markovian, and there could be an element of redundancy in the dynamics and the physics at lower levels associated with those causes. And, I think that that's, that's a perfectly fine way to resolve that problem. With mine, so, my primary motivation for exploring this was, is there a way to maybe just extract some principles from IIT about how the thermodynamics of information might operate and model them on more complex systems. That was my motivation. So next level up in complexity is a long path, and I'm still using a Markov chain. Obviously, there's some statistics here about, how many neurons there are in the cortex, how often they're firing, how long it takes a conscious intention to form. There is not going to be a stationary distribution over the brain throughout the day, but I sort of just, as an initial first guess, maybe over this first second, we can use a Markov chain and look at its stationary distribution. And, well, I'll sort of see what I did in a second. So the other thing that goes into this is that the way neuroscientists study information in practice is they look at a statistic that unfolds over some long path. So we could look at the empirical mean, and I did look at the empirical mean and found some stuff, but the pairwise empirical distribution ended up working a lot better. And, when scientists use statistics, there is an assumption that they capture the necessary information. So maybe it's warranted, maybe it's not. We're taking as a working assumption that this pairwise empirical distribution over the long path captures the necessary information transfer within the system to understand, how consciousness unfolds. So how do we take the sort of procedure that was IIT inspired, based on the IIT algorithm, applied over paths? Well, we extend our transition network over a longer period of time. And then the Maximum-Calibre ensemble, I chose to use a time invariant measure because there is a good chance that T itself would be variable. If you're looking at some part of the system that has a constraint over the path, so we're thinking of this path as the moment of time over which the conscious moment unfolds, you would end up solving the Lagrangian basically by tilting its transition probabilities to align with what was observed, due to the fact that pairwise empirical is a sufficient statistic, and therefore the parameters, which we'll discuss in a second, are natural parameters. And so, thinking of the observed difference again, you end up with information being T times KL divergence between pairwise empirical distribution, and then this would be the empirical mean, times what should have happened by the underlying transition probability matrix. So something I should have clarified actually is that what we're doing is we're taking the TPM as sort of a statement of the system's internal internal rules, internal laws. That doesn't necessarily correlate with how things actually unfold over time, maybe due to high, internal stochasticity, or maybe for other reasons. And then sort of our integration ends up being the sort of partitioned empirical entropy rate subtract the collective empirical entropy rate. So empirical mutual entropy rate, times by T ends up being integration. Okay, finally we're getting to FEP. sorry for the long time to get that. So the initial goal of this exercise was to expand out IIT's mathematics, think of it from a MaxCal perspective, and I thought I was done, but then I learned of the dualism between FEP and Bayesian mechanics. I'd already been exploring, vague free energy ideas in IIT, so I, just on a conceptual level, really. So I just wanted to explore this out of curiosity. Okay, so a few things. I read Bayesian Mechanics and, a lot of the papers. This was one paper which I read. Sorry, 1 second. Basically, the fact that it was over continuous time and state space, if there's any legs to the idea I'm presenting here, then I would love over time to find some sort of marriage between the two ideas over those continuous paths. It didn't seem sort of possible to reconcile in this situation while retaining the level of complexity that I was desiring. So the next would be discrete state spaces, partially observable Markov decision processes. This was one paper which I read on it. Again, like basically, I really love the mathematics, and in the future, I would absolutely love to see if I can find a connection between, what I've come up with and then active inference in its precise sense in partially observable Markov decision processes. That being said, some of the differences, such as sort of the way probabilities were defined, the space over, it didn't seem immediately clear to me how I would sort of square the circle. And at this point in time, I'm only, I don't even know if it's going to work out. So I decided to take a look at the early free energy principle papers and see if I can just map to the mathematical formalisms which are in those. As a first exercise, and so there's a couple of things. Obviously, FEP models biological self-organization. Even though I was going for the formalism of the unifying framework, I was trying to keep the spirit of active inference in mind as I did this. The 2010 paper talks a lot about homeostasis, and it got me thinking about, what is the purpose of predicting the exterior world? I don't think I'm saying anything new here, but I am sort of trying to justify the choice I made, or explain the choice I made, rather, by explaining my thinking here. So what is the purpose of predicting the exterior world? Well, basically, if we know what's in our exterior environment, then we can predict the future sensory signals which are going to come in, and we can predict what signals can come in response to actions as well. But, even just on this level, predicting the environment allows us to predict future sensory signals. And those sensory signals impact our future state. So in my mind, and very keen to get feedback on this, because I was genuinely trying to stay true to the spirit of active inference as I applied this. My idea was basically that there's probably a coupling between predicting one's own internal state and predicting the external world when you are something that exists in an external environment. And I was trying to keep this as general as possible as well. So it's not necessarily a person predicting the outside world. It could be a set of neurons predicting their immediately neighboring neurons. And so that's the logic which came into this. Alongside that, there's also the fact that there's a selection bias in that the states from the external world which have the capacity to disturb us and disturb our sensory processing those are going to be the only ones that we see and can model and are aware of by selection bias. So the way that the 2023 paper talked about external states which are of relevance to the system also went into my thinking there. So what I thought was basically, we've got this, so I was using just a sort of regular Kinetic Ising model for the IIT one. And I was inspired to do this by random neural networks. However, I also recently read Ishihara and Shimazaki's paper about state-space kinetic Ising models, and the model that they create to model neurodynamics is very, very similar. So I had a read of that and sort of checked how they approach certain things as well. So basically, my idea was that if you assume a normal distribution over the weights, biases, that's the language I'm using, over the parameters of the Kinetic Ising model, then what you essentially have is arguably an internal world model, or a approximate inverse world model. And I guess I'll sort of explain why. Given any fixed set of parameters, you get a rate function imposed over any set of path statistics, really, over a long path. But there are some which work better than others. For a Markov chain, the sort of a very good statistic to use is the pairwise empirical distribution. In the absence of any sensory data, these internal parameters are going to be wholly determining the dynamics of the system. And so they're serving a generative function in the sense of they're determining the dynamics. And then I would argue that you can also think of them as serving a predictive function, because what they do is they determine a range of outcomes that are kind of compatible or incompatible with the system's own internal goings on. And that can be modeled as a probability distribution by the rate function. So the idea is these generate, and they serve a generative function regardless. But then as sensory data comes in, that's going to change the pairwise empirical distribution that's actually experienced by the system. Is going to create a discrepancy between internal variables and observed paths. And so if we were to propose or speculate about free energy principle applying within this model, what I would suggest is that maybe the system tries to resolve that discrepancy by changing its internal variables, and that this can be understood as a approximate posterior distribution. And I started with a Dirac delta posterior after reading Millage and Seth's formulations of predictive coding, though I also explored normal. Just checking if there's anything else to... So what you end up with is you actually end up with this, the T times the KL divergence. And I know it looks quite convenient. It was actually an accident. I was learning a lot about this as it happened. But nonetheless, this is due to Einstein's fluctuation theorem, that there's this relationship between deviations and entropy. And also, so I probably should have clarified what this rate function characterizes is it characterizes how likely this pairwise empirical distribution is to happen when the system is, actually in equilibrium. So my idea was that as the sensory data pushes it out of its internal balance, that maybe the rate function that's imposed, or from the internal perspective of the system, maybe one could suggest that it's sensed as some sort of disturbance, explained or unexplained. Another way to motivate this, though, funnily enough, would be the Chernoff-Stein lemma. So, you take its internal variables as generative, as predictive, and then you take internal variables plus extrasensory signals as, the true generative distribution. And then the error term between them both should tend towards this value as well. So this is what you end up with the Dirac delta posterior. I would suggest maybe that there's room for interpreting the integration metric we discussed earlier under the lens of a certain amount of VFE, which once the parameters are optimized, can't actually be reduced by further parameter adjustment. It can only be reduced by changing external sensory inputs. And the interesting, so just to demystify this a bit, this is simply just the surprisal over the whole path. Because it's in my nature to think about things from multiple mathematical angles, you can also think of this as a data set, and you can think of this as a loss function. You can think of this as a L2 regularized loss function, and it characterizes all of the, it captures all of the parameter dependent parts. Now, obviously in practice, the parameters are playing a role in generating the data. We will get onto that part in a second. For now, we're kind of, I wouldn't say we're thinking of them as separate, but we're thinking of this VFE function or this loss function as sort of modeling what would happen if the parameters had been at their final value the whole way, is how I would think of it. Due to the conditional independence of the probability matrix, and then also independence assumptions about the distribution of the parameters, we end up with a factorizable loss function, which is good because it means that we can just look at one single node and see what happens there. And we won't get a complete picture of what happens across the whole, but we will get an understanding of how the optimization dynamics play out. Before we look at that, just a quick note on normal stuff. You end up with precision-weighted uncertainty terms. Is going to relate more to expected loss. However, this part remains the same because it's not directly dependent on the parameters. And then, yeah. Okay, so I think there's still a few holes in this approach. And that's because it is theoretical, really. Like, it's been motivated to find some sort of way that I could relate the mathematics of IIT and VFE to each other. But that, that doesn't necessarily, that's a very top-down view. So I wanted to understand what this might actually look like from the bottom up. Is this even viable in the first place? And given the equivalence to a supervised learning problem, I decided to just ask, what happens if we apply stochastic gradient descent here? motivated by the convergence theorem between stochastic gradient descent and gradient descent in certain contexts. Obviously, this model is generating its own data set, so it's a bit of a weird one. It's, we would be training on something that's actually being generated by the thing that's training. So it's not obvious whether or not it will work out. I decided to do the maths of what it might look like within a single node that's not receiving any input. Obviously, it ends up collapsing to just, this would be supervised under this frame. But what we do get, so this is our starting point, we get mean reversion. We get the derivation for this initially. I believe there are a couple of mistakes I made. However, it fit with the empirical results I observed. So I've kept it in here. You can get a terminal variant when you look at dynamics. And since it's not receiving any sensory input, we presumably want this, which, maybe this could represent a posterior variance. We want this to be equal to our prior variance. And so from that, you can get a relationship between time and the learning rate that should be, if you have a fixed learning rate, this should determine a sort of fundamental time scale over which we're assessing our VFE functional. The other thing you can do is if you just treat this as one parameter, the eta times beta, beta is regularization strength. And then you can use the sort of different equations to basically get a dynamic eta and a dynamic beta at each step. And you can see the impact that has on the dynamics as well. Next one I looked at in mathematical detail was the recurrent case. And you do get mean reversion, but something to flag is that the variance is very different. And also you shouldn't be assuming independent. I don't believe this undermines the factorizability because it's just independent between a single node's own parameters that seems to break down, but it's worth flagging. That's not something I fixed yet, but I just wanted to flag it. So what happens? Basically, you get these spiking patterns. So, and if you set eta times beta to be between 1 and 2, you can get these dips, which, maybe could potentially model some sort of refractory period. I was just reading about how spiking is sometimes modeled today. I was quite pleased to see that sometimes it's, you have a logistic over the voltage times noise. And then this was the recurrent one where it's, it's generating its own input. So these were the plausible frequencies. I also explored some implausible frequencies. In both ranges, learning occurred. So in this case, because it's not receiving any sensory input, we would want it to learn its own priors, its own equilibrium. So at the top, we've got what it does when it starts in equilibrium. At the bottom, we've got what it does following a disturbance. And it seems to do that. So then for slow learning, because so basically these update rules, so now here S is the inputs. So this is just a node receiving inputs, potentially from other nodes, potentially from itself. This comes from differentiating the log sigmoid. I believe that these can be interpreted as prediction errors because, they're the probability of the incorrect prediction, the one that didn't happen. 1 minus xt. I use 0 and 1 as the values in my Ising model. However, if you want a more traditional link, then the biases and weights, you maybe assume a normal prior over those. And I always think there's two ways you can motivate things. from the top down or from the bottom up. So the top down motivation would be maybe thinking of the long path as, a series of small paths, and you think of each one maybe as some sort of batch potentially. And then you can say that that when the fast posterior updates, that constitutes a sensory data imposed observation, which then is fed into the higher level prior. In terms of now we're going to model this from the bottom up, I thought it might be a bit more plausible to just have them update synchronously, but have a drag on the slow variable. So these were the update rules. And obviously it's consistent with MSE or precision weighted MSE, but then it's also just coming from, normals. And one thing I observed when I tried this, so it was very parameter dependent and hyperparameter dependent. So sorry, I probably should have explained before, but on this one, we've got the error for the weights, the error for the biases, fundamental bias term, fundamental weight term. And then this would be the sort of the slow prior, no, fast prior. Sorry, fast prior would be here. And then the slow priors would constitute the parameters. Nonetheless, what we sort of see is that some sort of self-regulation in this was able to be achieved. Also mean reversion and learning observed. So that's kind of just a repeat of what we saw before. And this is just a single node without any weight being fed in, and it's over each of its well, you can see that this one's slower, it learns slower. That's the slow updating one. You can see that when it's in its equilibrium conditions, it follows a wave-like pattern. I also wanted to see if it could learn different types of sensory input. So there are a few different ways I did this. Sometimes I did it as you just change the value of the node in an unexplained way. Maybe that maps to hidden. And sometimes you do it as sometimes you do it by feeding sensory data into the the edges, which are supposed to maybe potentially represent the synapses. And what you see is that if you feed it consistent input, then it ends up learning in a different way to if you're feeding it noisy input. So this isn't 100% noisy input. I've called it structured noise because it's stable for a while, then it changes, then it stables, and then it changes again, and it does so unpredictably. And there's just some interesting effects on the dynamics. I see that I've got
Alex,
very little time. Yep.
Alex, I have to ask you to wrap up in the next few minutes or so, if that's okay.
Thanks. Yes, right at the end.
Okay,
right at the end.
Perfect.
So yeah, I just wanted to take a look at if different schemes could be replicated. So I talked before about how you could potentially make the learning rate dynamic, depending on the different equations. And what I found was that in the plausible regimes, there was sort of more elasticity of the parameters. And that in the implausible, 730 Hertz regimes, certain like highly dysfunctional metastability seemed to get downregulated a little bit. I also tried a traditional predictive coding circuit. And what I found, long story short, is that it was capable of learning, and also that it did so it was more stable to dysfunctional input than the other ones that I had tried. And then I also wanted to see if filtering could be done by feeding it different types of sensory input, starting from a position of neutrality in the weights. And what I saw is that filtering did seem to happen. However, I haven't necessarily nailed down how that happens yet, or what drives it. So some concluding remarks. Basically, I do have a few further questions: computational, biological, theoretical, and just if I had infinite time, where I might see it going. And then, yeah, I guess just final thing to note is I know that there's so many differences between each of these theories, and there's so many things that make them specific. And I'm deeply inspired by all of the differences and specificities of each theory. I also think that there is room for overlap. What I'm trying to say here is not that there's any you know guarantee even of overlap within them, but that I just think it's worth exploring, worth entertaining, and that I do believe some nice maths has arisen from it. But I'll see what you all think. Thank you very much, and yeah, questions.
Great. Thank you, Alex. If anybody has a question, please raise your hand or just speak out. That's fine. Okay. Well, if there are no questions now, perhaps we can hand over to Carl. And if anyone has any questions that come up, they could uh, raise their hand a bit later.
You don't want to ask me.
I might hand over to you, Carl.
Well, no, I want to say Dalton and Maxwell should ask one question each.
Okay.
Of an illuminating sort.
Hey, folks. Alexander, I really enjoyed your talk. You probably, I mean, you referred to some of my work. So I spotted your paper in the wild. Actually, it's funny. We were discussing it at Numinal internally a few days ago, and it kind of came up like, "Hey, did you see this cool TNB presentation?" So, I mean, I've been working on similar things that I can't talk about right now. Having said that, I was going to write you anyway to say you should get in touch with me, and there's a lot to discuss here. I mean, I've been involved in almost everything that you have pointed out, the inner screen model of consciousness, applying this. I think Dalton is the one. Hey, Dalton, nice to see you, by the way. I think Dalton is the one who really introduced the MaxCal angle to the free energy principle literature, and we've been doing, I think, a lot of cool work in that direction. So, I mean, in any case, great presentation. I don't have specific questions now, but I mean, do write me a note, and maybe we can meet up and discuss this stuff. I have some projects that I'm preparing right now that you might want to get involved in. So just shoot me a note. My email is easy to find.
Thank you. That's great. I've read much of your work, and I'll definitely be in touch.
Well, that's it. That's exciting to hear. Looking forward to hearing from you.
Thank you.
Okay, I think that means it's my turn now. Well, thank you. Firstly, it was very thought-provoking. I had a lot of questions and comments, but I'll, in the interest of brevity, perhaps email you and we can discuss not when everyone else has to sit through it. Uh, I think so. Perhaps the biggest question that I had was uh, why necessarily structure this as a maximum path entropy problem if what you're mostly interested in is the conditional entropy between two nodes? It wasn't clear to me that you required actually a path or a continuous or discrete chain of states all at once. Like you were mainly looking at t plus one given t. So did you gain anything specifically by thinking in terms of maximum path entropy, or could this have been said in the terms of conditional entropy or conditional mutual information or things of that nature? And the reason I ask is because there are very interesting information theoretic statements that one can then make based on, for instance, the work of Shannon and um, later information theorists on specifically this. Jeffries has a lot of material about how conditional maximum entropy is like Bayesian inference. Um, so with that slightly different language, a lot of stuff is opened up. So I was just wondering if the maximum path entropy is that really essential, or can you just get away with conditional entropy?
Honestly, I think that that's a really good question, and probably the first thing I'll do after this talk is take a look at exploring it from a sorry, my brain's slightly blank.
That's okay. That's all right.
From that point of view. Um, what I will say is I will explain my rationale though, as I still think there's something to be gained potentially from the MaxCal view, but I will have a look. And that would be that I would say on the FEP side, it's less clear whether MaxCal is necessary. From the IIT side, there's a lot of kind of thinking that the community there do in terms of what is the inside point of view and what is the outside point of view. And one thing that I didn't include in my talk, but it's in the back of my head, motivating the way I think about it, is that different conscious moments happen at different speeds. So the amount of time it takes me to see something is much faster than the amount of time it takes to think through something. I think there's also some interesting points about how maybe this slower order cognition could even build on top of the faster cognition. So if there is one thing to be gained from the MaxCal perspective, potentially, I would say that it would be the time scale. And maybe this is a maybe, I really need to look into it more. Maybe the canonical time scale I identified over which inference should occur, maybe it provides a principled way of deciding on the time scale, and so don't necessarily need MaxCal to implement in that time scale, but maybe for setting the time scale up. But I'd really need to look into it more. Those are the things I'll mull over when looking through it in more detail.
Sure. Okay. Thank you. Thank you.
Okay, thank you, Dalton.
Just
and Maxwell.
let me make one last comment just on the side. I'm going to put my email in the chat box. If you want to write me later, I'd be happy to answer questions or start a conversation. So you'll have that if you look in the box. Sorry.
Thank you so much.
Continue.
Great. Thank you, Dalton. Okay. If there are no further questions right now, then I think we will hand over to Carl.
Good. So it's my turn now, is it?
Yes, your turn now, Carl.
Excellent. Good. Well, thank you for a lovely presentation, and also thank you to Dalton and Maxwell for their offers of ongoing support. That's very nice to hear, and the raison d'etre for these meetings. And my support, or our support, really depends on how we can best help. I'm going to ask you some very, very simple questions. This is a PhD work at the University of Oxford, is that right?
Oh, so no, actually. So my first work was master's. Then I I went into the wrong career after graduating, and couldn't really let go of this obsession. So did quite a lot of it on the side. Sought some informal feedback from my former supervisor, and my like just other people in my network, and because it's been a while since I've been in formal education, what I decided to do was just write out the ideas, put them out as a preprint, and then the goal is that I've done something recent when I hopefully do a PhD and I can go through these ideas in more refinement.
I see. So your ambition then is to do a PhD. Can you get back into academia?
Yeah, or maybe, a research position. I'd love to do research on cognitive science. So a PhD seems the best route. However, it's my goal is just research full time.
I understand. Yes, no, I'm sure you're absolutely right. Okay. So I had thought that you were sort of doing a PhD now, and that matters in the sense of the kind of feedback and the agendas that you need to meet in order to complete your PhD. But now it's more the agendas you need to meet to apply for a PhD or to engage people like Maxwell and Dalton, in another kind of institution. And it struck me that, just summarizing the work that you have presented today, there was one agenda which could be described as basically joining the dots between IIT and Maximum-Calibre principles and the free energy principles and other takes on that, which would include the thermodynamics of prediction, thermodynamic computing, predictive coding, and so on. And then there was another chunk at the end, which was basically numerical studies, intuition building, after committing to a particular dynamical system, in your case, an Ising model, and then building intuition by doing numerical analyses with a particular focus on the separation of temporal scales and how they can be interpreted in relation to various learning rates, for example, or precisions and temperatures, and what kind of overall principles would emerge from those numerical studies. Would that be a fair summary of your what you told us?
Sorry, my brain's slightly tired after the presentation. Yes, I think that's a good summary. The starting motivation was, maybe I can find a connection of some kind between FEP and IIT, and then as it's unfolded, I just became very interested in the Kinetic Ising model because of all these nice properties it had, the state-space Kinetic Ising model. And then the numerical stuff is actually, that stuff's pretty recent. I thought about maybe submitting something to something and didn't manage to get it done. I had a couple of other things on, but in writing, I explored the supervised learning view, and then after realizing that stochastic gradient descent might actually work, that's what motivated the empirical domain. So yeah, I'm sort of I hope I've answered your question there.
Yes, okay. Well, I'm just trying to get a feel for what kind of feedback would be useful for you. So the way that the feedback that I will offer you, and it may or may not be useful, and you don't have to pay attention because this has been recorded. So I'm doing this largely for the recording, so you have a resource should you want to go back and listen to it. So just very generic but hard advice. You're not going to be able to gracefully publish this kind of work until you have an academic affiliation. There are too many people out there at the moment who've got bright ideas and want them to be endorsed or acknowledged for you to get your foot in the door. So you really do need to find an affiliation so that you're writing from an institution that endorses the kind of material you're producing, just to get your foot in the door with an editor, for example, to avoid desk rejection. So I think is imperative that you do take serious. If you want to do this, you've got to commit to it. And that basically means finding a research assistant or a place in an R&D term at R&D group in industry, or ideally a PhD. That would be wonderful if you could get a PhD. Second, you have to think carefully about how you use these numerical analyses. You have to make a point. It's a fine building your own intuitions, but if it doesn't tell a story that somebody can listen to and get something from, they are useless. So you need to be able to decide what do you want to tell the reader, basically, or what do you want to tell a potential supervisor when applying and encouraging them to accept you so you can apply for funding to do a PhD. And I think there is an easy way to do that. So I'm saying this to motivate and contextualize my feedback. A lot of my feedback, though, is really for framing the denouement of the PhD in terms of putative links of the kind that you've already identified in your final slide between the different ways of looking at self-organization in things that may or may not be conscious, or the introduction to a PhD proposal, saying that, look, all of these really interesting, potentially promising perspectives on building systems that self-organize in the right kind of way can be looked at through different lenses, and yet basically there's a cross-cutting theme here. There's an underlying calculus or physics that basically ties them all together. So that would be the joining the dots part, which you started off with the IIT and the free energy principle to a certain extent. What I'll do is I'm just going to whip through a number of papers which I think you'd enjoy reading, not to try and simulate or borrow the maths, but just to know there are these different perspectives so that you can nod to them in a narrative, either proposing a PhD or at the end of your PhD saying, look, these are future directions of travel. These are interesting and fecund areas that we could join together at a later stage. Before I do that, before I give you my stream of consciousness, I have to say that focusing on IIT is a challenge, because to my eyes it's a bit of a moving target, and that came across in sort of versions 2, 3, and 4, and even 4 was slightly difficult to reconcile with the maths that people would normally bring to the table to formalize these notions and to make some analytic statements or assertions So my advice is to acknowledge that the IIT, is not written by mathematicians. It's written by extremely bright life scientists, and it does change. So don't over reify the maths of IIT. It may be that it doesn't quite exist at the present time as would be understood by a mathematician. Having said that, I do think that if you can establish cross-cutting themes, a lot of people will be interested. Um, uh, um, so it's certainly worthwhile putting IIT out there, but I just hesitate to think that there is going to be some definitive calculus that's going to gracefully unite IIT and the FEP, for example, simply because the maths of the IIT is just not written in the kind of way that a physicist or a pure mathematician or applied mathematician would be able to articulate or use. And don't tell anybody I said that, because Giulio Tononi, was my best friend when we were in California together at the inception of all these ideas. So that's just private between you, me, and the recording. Having said that, let me share the screen. Yes, I'm trying to remember all your questions, but for the sake of time, I'm going to request control. So you should now be receiving, please surrender your control.
Oh, how do I do this? I guess I enter.
We'll have to have our chair. Let's try. Oh yes, no, you've clearly done it. Whatever you did worked. Okay, so hopefully you can see now my screen. Yes, I know that. That's the whole point. Sorry, my screen's talking to me. Right. So Dalton or Maxwell mentioned the work of Kate Jeffrey, and I thought I'd just put this up just to sort of give you a concrete pointer to what I imagine the work was that they had in mind. Interestingly written with Carlo Rovelli, who's somebody who tells compelling stories about relational quantum mechanics, which will become relevant later on. So I haven't read this paper for a long time, but I do remember thinking, oh, that's a really nice way of looking at things. It addresses issues beyond what you're dealing with, but I think it's a narrative and a perspective which, Dalton's come on. Dalton, did you want to say this is the one you wanted, or was it another one?
No, I wanted to say it was another one. I was referring to the work of Richard Jeffries on
right.
Jeffries
Well,
conditioning. Richard Jeffries, he has this generalization of Bayes' rule of conditioning, which
Jeffries Priors, good grief.
yes,
Right,
exactly.
historical Jeffries. Oh,
Yes,
right.
exactly.
Okay. Yes, sorry. Right. Well, we don't have time to get. Sorry, I misread that. I thought you were talking about Kate Jeffrey, which surprised me because Kate's not a mathematician. I think she's a psychologist or no, a neurobiologist, a neurophysiologist. But Carlo is a sort of, I think a more credible formal theoretician. Jeffrey's Prize, yeah. So they would be the statisticians' Jamesian prize, wouldn't they, basically? Yeah, sort of those least constrained prior beliefs. Good. Okay. So, well, don't ignore what I've just said, because I still think that this particular paper was interesting, and it will introduce you to the to a certain extent to the writings of Carlo Rovelli, who's a very good popular writer in this space. So that was that. Why is that relevant? Why is relational quantum mechanics relevant? I think it's relevant in the following sense that if you're starting from the point of view of self-organization as read through the free energy principle, or more generally, sort of the physics of self-organization, then you are, by using the word self, implying that there is something that is not self. So you're immediately applying a bipartition to state space. And that's absolutely crucial, because once you've got a bipartition in place, you can now talk about the mutual information. So no longer are you stuck in the 20th century of Shannon information, the entropy of a particular set of random variables. You're now in a position to talk about the relationship between one subset in a bipartition and the other subset of the bipartition. And the obvious way to talk about that is the mutual information between the two. So you're now talking about information of a relational sort, which now allows you to talk about the information entailed by, say, the states of the self in relation about the states that are not yourself. And that's a crucial move. So most of the interesting things, information theoretic treatments of self-organization, are all about relative entropies, which is why I emphasize relational quantum mechanics. It's the relative entropies that matter. You've written these down as KL divergences. You can do a little sort of detour into Wasserstein metrics if you want to, but do not do that. Stick with KL's relative entropies, extensive quantities, because that's what you're going to be using. So everything has to be articulated in terms of relative entropies. If you add a cross entropy to a relative entropy, you get a free energy. So at the end of the day, you're going to be talking about free energies. That's the right kind of information theoretic structure to talk about, but it does rest upon having a partition of states. So that now what you have to do is to appreciate that much of 20th century work does not consider that. It just doesn't care. Shannon doesn't care about the relative entropy. He just cares about the entropy of some random variable. Of course, implicit in things like rate distortion theorems and implicit in sort of mutual informations and relative other formulations in terms of algorithmic complexity or transmissions, then you've got inputs and outputs. And as soon as you have inputs and outputs, you've now got, or things transmitted and things received, you've now got another bipartition. But the foundational maths does not apply to, does not admit a relative entropy until you've got a bipartition, which means you've got to be quite careful in interpreting MaxCal and max entropy things, because they did not make a clear distinction. They weren't dealing with the bipartition. They weren't dealing with information about things. However, as Dalton has shown, you can posit a certain, you can suggest that there are aspects of the MaxCal, constrained MaxCal principles that are dual to the free energy principle. And the constraint gets really important here. And in my world and in my view, the constraints just are the generative model, and the generative model is just a joint distribution over this bipartition. Which means what's the entropy got to do with? Well, it's the entropy of the measurement, and you want to maximize, in the spirit of Richard Jeffries, the entropy of any measurement where measurement is read as an inference. That's slightly paradoxical, because most people come at this from the point of view: how does self-organization resist the second law? If you're resisting the second law, which of course doesn't account when you've got this bipartition because you've got an open system now, aren't you surely trying to minimize the entropy? Specifically, the entropy of the way that the outside influences the inside, the data, for example. And so I think there is a certain pressure on people who like to think about these issues to explain the paradox between minimizing the dispersion and the entropy of your states as exposed or in exchange with the heat bath or the world, and maximizing the entropy of something else. What is the other thing? What entropy are you trying to maximize? And of course, it's the entropy of the information about the outside. That's in the spirit of Jeffries and Jaynes. When you're reading Jaynes as a physics of measurement. I quite like this paper where basically James tries to recognize or tries to explain this almost paradoxical yin yang that if you commit to a constrained maximum caliber principle, you are implicitly also committing to a minimum entropy production principle. And that minimum entropy production principle inherits from the theory of dissipative structures due to Prigogine. So he's now trying to reconcile the work of Prigogine on self-organization in open systems, in non-equilibrium systems, or far from equilibrium, with the measurement physics implicit in a constrained maximum entropy or caliber context. So I'm putting this up, just as it is interesting to see James wrestle with this and sort of repair that dialectic, which has always occupied me and everybody that I know who asks these kinds of questions. So I thought it might be nicest to mention, cite, and read that, so you understand things from his point of view, and implicitly also Prigogine's point of view in terms of self-organization. Another one I thought, well, no, actually, no, that's no. Yeah, another perspective that you covered. No, let me go in order. Let me confuse myself. You started talking about sort of self-organized criticality at one point. That's another field that you should certainly want to join the dots with, but it's also an extremely phenomenological field. It's a descriptive field. There's no physics behind self-organized criticality. There's lots of observations and hand waving about scaling laws and the like. However, if you drill down onto or apply the maximum caliber principle or the free energy principle, let's assume for the moment they are dual, then you get self-organized criticality for free at the point that you get this free energy minimizing solution or maximum caliber constrained maximum caliber solution. Why? Well, it's really simple. It's just the dynamics, the paths on your Lagrangian. I thought, I got the impression you were trying to write it down as a Hamiltonian at one point, given the symbols you were using, which just is the variation of free energy in the limit. Are determined locally by something called the Lyapunov exponents, and they can be related to the curvature of the Lagrangian or the free energy landscape. That curvature determines the eigenspectrum, and the expected eigenvalues of the eigensolution are the Lyapunov exponents. The Lyapunov exponents control how the degree of self-organized criticality in the sense of critical slowing. So you get long-term memory. Things decay very, very slowly, speaking to your focus at the end on the separation of timescales. So what you're looking for is a physics explanation of why things have a natural tendency to organize themselves such that their eigenmodes, their eigenfunctions don't dissipate very, very quickly. And using that phraseology means you can now talk about the theory of dissipative structures as read by Prigogine. So you're now looking for a description of systems that don't evaporate, dissipate, or disappear almost instantaneously, which means that their Lyapunov exponents and implicitly the eigenvalues of their dynamics, specifically the Jacobian, approaches zero from below. And that is guaranteed when the curvature of your Lagrangian, in a pathological formulation, is small. What is that? That's basically when you've got the maximum entropy. So the maximum entropy, or the maximum caliber over a path, just is a statement that the curvature or the Hessian governing your dynamics is such that the accompanying Jacobian will have lots of eigenvalues that are approaching zero from below, which means that, or the real parts will approach zero from below, which just means things are persisting for longer. They decay, they don't dissipate almost immediately, which means that they have measurable states. If things dissipated instantaneously before you can measure them, you're in the world of quantum physics. However, if things persist and have characteristic states that are measurable, they must last for a finite amount of time. And that means that the eigenvalues, or the real parts of the eigenvalues of the Jacobian of the dynamics, have to be nearly zero, which means that the Hessian of your Lagrangian or your Hamiltonian or whatever you want to call it. In my world, it would be the free energy functional, has to be sort of flat and basically allow for this sort of long-term critical slowing and self-organized criticality. And that can be, using numerical analyses, that can be demonstrated in the context of perception. So when you change the curvature or the Hessian of your free energy landscape through adjusting the precisions in the right kind of way, leading to the notion of balance synchronization, then you can induce self-organized criticality simply by presenting stimuli numerically to a system. So this paper just takes you through the underlying maths, but more specifically then commits to a numerical analysis using not an Ising model, but using a nested Lorentz systems. So they've got autonomous dynamics in them, but it's continuous. So it's a predictive coding numerical simulation to show that processing stimuli, perceiving things from the inside necessarily entails a self-organized criticality that can be measured in all sorts of ways, from fluctuations in the free energy through to the Lyapunov exponents. My suggestion is you do this kind of numerical analysis for your Ising system. And use the numerical analyses to show that self-organization, or certainly critical slowing, is an emergent property of any self-organizing system suitably constrained in the spirit of Jaynes, or from the point of view of the FEP, with the right kind of generative model that can fit these sensory inputs. So that's why I put that one up as one example of that.
Thank you. Yeah, that's interesting because in some of my other analysis, I found that the information metric I had was related to the spectral gap of matrix. So be interested to see if you can
For those people who don't know what the spectral gap is, it's the numerical difference between the smallest and the next smallest, or spectral radius eigenvalue. And if you close that gap, sometimes you have two or more of these what are called unstable modes. In synergetics, they would be called order parameters. So as you flatten the eigenspectrum, and therefore close these gaps, then the probability that you'll have lots more of them near zero, so things decay very, very slowly, increases. Excellent. Okay, well, exploit that. That would sort of, if you like, engage the self-organized criticality community and people who understand statistics, for example, in terms of Jeffreys priors and psychologists who sometimes think about attention as setting the temperature or the precision right to enable you, and then you can talk about ignition in global workspace theory, and then you can relate that to IIT should you want to. There are all sorts of opportunities there. This is the only one paper that I've ever been involved with, made an explicit attempt to reach out to IIT, but not at the level of the maths. I repeat, from my perspective, that would be a bit of a challenge. But you can certainly sort of reach out to the axioms that underwrite IIT and just see, are all of these weakly speaking consistent with a constrained maximum-Calibre principle or the free energy principle? And a stronger statement would be emergent properties of. It could be no other way. And this is a bit of a narrative account. It wasn't written with mathematicians, but it might be an interesting read for you simply because it does explicitly have a section on integrated information theory. Where is it?
Yeah, I believe it's right towards the end. Consciousness and
Oh, you know
integrated.
that. Oh, there you are. You
Yeah.
know that better than I do. Okay. So it just goes through sort of the axioms that Giulio has consistently referred to in motivating various formulations of IoT. From a sort of from the perspective of this feedback, this this treatment turns upon this relative entropy or relational aspect simply because you've got two information geometries in play. So we could talk about that self-organized criticality in terms of the eigen solutions to the Jacobian and the curvature of your Lagrangian, or you could talk about it in terms of information theory, because once you've got a distinction between the inside and the outside, you can now posit, once you've got a bipartition, once you've got the opportunity to talk about the relation of how one thing stands in relation to another, you can now associate the internal states, the first person perspective, with a belief about the external states. So, just inducing an information theory or a probability theory simply by saying that the internal states have beliefs about something else and external states, simply because every value of the internal states there is a morphism to a conditional probability distribution over the external states that immediately equips the space of internal states with an information geometry with a Fisher information metric, which is really interesting because there's another metric space, which is the probability of the internal states in and of themselves, which is the thermodynamicist reading. And that you can get access through the work of people like Gavin Crooks, for example, who I'll mention in a moment. That means there are two information geometries in play. And as soon as there are two information geometries in play, you can start now to talk about sort of monisms and dualisms and the like, simply because you've got two information geometries that you can read from the point of view of dynamical systems theory and self-organized criticality, but also can be read from the point of view of information theory. And yet there are two. There's a physics of the brain, and there's a physics of the outside being represented by the brain. And they both rest upon the same substrate and the same maths. Again, speaking to the importance of having a partition between things in and of themselves and things that are represented or encoded or however you want, inferred, measured. The things that are measured. So a distinction between the observer and the observed has to be in play before I think you can talk sensibly about any maths of sense making or indeed consciousness. The Gavin Crooks, I don't know if Maxwell is still here, Dalton's still here. So this is, he would be one of the sort of heroes of the thermodynamics of prediction, and has written very, very concisely, very beautifully about information theoretic or information geometries that underwrite thermodynamics. And partnered with Suzanne Still, I think is in Hawaii, I'm not sure. And also with the inventor of independent component analysis, a very practical device that implicitly rests upon Jeffreys-like prize, but of a certain sort. Just to write this, I'm sure it's been published somewhere, but I've just put this up because that's the key thing, the thermodynamics of prediction. I think you'd enjoy reading that, simply because it sort of ties together the thermodynamics read in the sort of 21st century by people like Gavin Crooks with the predictive aspects that you might see in predictive processing, predictive coding. In fact, Suzanne Still really takes her view of prediction more from the point of view of something called the information bottleneck approach, which is almost isomorphic to where you started with sort of ABC t-1 now and the future, and that would be one view of the information bottleneck. The view that we would take would be that the present is a Markov blanket that separates the past from the future, and therefore the past has to get to the future through the present, which is the bottleneck. But the maths is the same, lending you now an opportunity just to reach out or mention, or even discuss if you want to, the thermodynamics of prediction as read by these scholars and these authors. We have another one we didn't know. So Suzanne has written. Suzanne still has written about this, since 2010 and the like. But this is, I think, a little bit later. Oh no, sorry, 2012. She has subsequently written work that involved Tali Tishby. Tali Tishby died about 5 years ago, but he was the author of the information bottleneck, which is another information theoretic formalism of exactly these issues, which it would be nice to sort of bring into the fold as another way of joining the dots. They're all the same thing, but using different languages. And here's another example of the same thing. It is the path integral formulation of the free energy principle. And one has to ask, where does the minimization of entropy get into the game? And this, where does it get into the game? It obviously gets into the game in terms of maximizing your entropy under constraints. So here's your, what does it expect? There's a free energy one. Anyway, you can read this in the usual way. Here's your entropy here. So this is your energy constraint, and this is your entropy, noting that the constraint rests upon a joint distribution over, or in this, yes, it's a joint distribution separated into a likelihood and a prior, a joint distribution over the external states and the in this instance the Markov blanket states that sort of connect the inside to the outside. That's what I meant by the constraints just are the generative model, where you're reading the generative model formally as a joint distribution over cause and consequence. That is the cause-effect structure in the free energy principle. Why did I put this up? Yeah, because it is formulated in terms of path integrals. But this one cheats in the sense that it works in generalized coordinates of motion, so that the action now becomes a Lagrangian, or you can write it as Hamiltonian should you want to. And the maths becomes really, really simple. And it is in continuous state space. So it wouldn't easily accommodate your Ising. I'm presuming the Ising model is about discrete ups and downs, is it, or is it not?
Yeah, so the Ising, the state space kinetic Ising model, I did over zeros and ones. I did actually read this paper before trying to understand how to fit active inference in, and obviously as in I'd really love to read more and see if I can potentially it could be seen where I've gone wrong in the discrete view as well from reading this and observing differences.
I suspect you haven't gone wrong. It's just you've got to work out what you want to show and just clarify it for the reader.
Carl, do you mind if I make a remark here?
Sorry, yes.
I said, do you mind if I make a remark here? And I think you didn't. I think you were indicating approval.
I was.
Yeah, I thought you didn't hear me, but anyway.
I can have a cigarette while you're talking. That's very good. Carry on.
Sorry?
I'm saying I can have a cigarette now. You've taken over. So please carry on.
Quite right. So when Carl mentions this might be difficult in the Ising model, there's a couple of different ways to nuance that. One is you can simply do some sort of extension or continuous modification. So you work discretely and then you extend the constructions that you're using over paths of Brownian motion, say. if you manage to email me, I'll explain a couple of these things to you because I have some of it written up in a different context, and you may benefit from that. The challenge would be the fact that you have to take some sort of scaling limit because your kinetic Ising model is in 2 dimensions, right? So you're dealing with actually uh, a sort of Markov random field. But there is a lot of very good work about Markov random fields, which you can just use straight away. You don't have to necessarily do a scaling limit or an extension theorem type construction or anything like that. Carl himself has a lot of very nice work on random fields, and there are these information field theory people that try and do Bayesian inference in these settings. Uh, so finding an appropriate random field whose fluctuations are resembling something like Kawasaki's updates for kinetic Ising model, that would probably have you in a much closer situation to what is in this paper. And I don't think it requires much technical overhead because a lot of these things have already been, well, the pieces have already been established. But Carl would probably be able to say more because he's been on the inside of doing inference about random fields.
Thank you. Yeah, I did originally try to fallaciously try to do in continuous extension, but ran into that problem, the scaling limit, because the
Yeah, you don't
as
you don't want to
so
do that unless you have a lot of time to learn a lot of things about probability and the analysis of partial differential equations. You don't probably want to do that. But
yeah.
luckily, I don't think it's necessary. I think you just use some existing formalism and it's much simpler than a mathematician would make it out to be.
Thank you.
Thank you very much. I mean, you know, I'm just mindful of Alan Turing. You know, that's where he started, but he didn't have computers. He had to do it all on pieces of paper. You know, sort of his sort of Turing pattern formation, and then later chemists came along, the BZ system, and then then we have all the Markov random fields. And interestingly, most of the numerical studies that underwrite early descriptions of the pre-energy principle have this sort of, as Dalton was alluding to, a local connectivity, and that's absolutely crucial because that locality means you've got a sparsely coupled system, which means that, as Dalton has actually proven, with almost probability 1, there will be a Markov blanket there, simply because of all the connections that could exist. Only a small fraction are actually present because I can only influence my neighbor, and hence the motivation and the importance of things like random fields and Markov random fields. And it's interesting, of course, you've identified probably the most important Markov random field, which is a long time. Everything you've done is basically predicated on the notion that there's a Markov chain in play, and hence your explicit referral to Markov decision processes. So that's all internally consistent. But what Dalton just said is actually really useful because that's exactly where I was going at a much less theoretical and more practical level. I was just thinking about how you could. Oh, before I do that, another, I think, useful historical paper that would allow you to see how all of these conceptual streams converged. So the free energy principle in and of itself is largely due to the Feynman-Jensen bound, or the Feynman variational principle. And this was first articulated in the 1950s in a rather colloquial context, but the idea is absolutely central to finding the right information theoretic functional that can be read through the lens of thermodynamics, for example, or in this instance, quantum electron dynamics. And he's just basically introducing variational physics, or the variational principles of least action in a particular context. That basically rests upon in your numerical studies, you're not actually going to be using sample distributions. You don't need to use stochastic gradient descent. You can use variational gradient descent, and that mathematically is a description of an idealized stochastic gradient descent. So the whole point of Feynman's work and the variational free energy is that you are describing a system at a sufficiently coarse-grained scale that would be the average behavior of an infinite number of stochastic gradient descent schemes, individually realized. So, that's really the gift of Feynman, and why people usually end up using variational procedures. Simply, it's just a description of, I repeat, an idealized or an abstracted ensemble behavior, or where the ensemble is constituted by lots of actual, say, pot samplers, Metropolis Hastings or MCMC, or lots of numerical stochastic procedures. So that's why it's so efficient, and that's why it's called variational free energy.
I do have a quick question, if you don't mind. I'm just curious about the variational gradient descent. Are there any circumstances where it either fails or works less efficiently, like maybe short time scales or something? I'm just curious, just because I'm really interested in all the nuances, that's all.
Right. So the answer to that, from my perspective, is no. The whole point of Feynman's variational principle is that it holds at every scale. So then that now becomes that induces a problem which you have implicitly addressed in your numerical studies about the coupling between different scales. But at each and every scale, you are just implementing a variational principle of least action, which I attribute to Feynman, simply because you're using a variational free energy functional as opposed to some arbitrary cost function or some other not some other function. So it will apply and should apply at each and every scale, and we have written about that in the context of the normalization group from two perspectives. One, in terms of building numerical simulations with separations and temporal scales of the sort you have done to now distinguish between inference and learning, for example. You would just apply Feynman's variational principle of least action to each and every scale in an internally consistent way, such that the slower scale provides the context of the faster scale, but the faster scale provides the sufficient statistics or for the free energy gradients for the higher scale. So you've got the circular causality, which you'll also find in synergetics and the center manifold theorem, for example. So the answer is no worries about that. You could have been asking me, well, if I commit to a variation, what is the essence of a variational formulation? Well, you are committing to a particular functional form for the probability distributions, which makes your life a lot easier, because now everything becomes analytic. All the gradients and curvatures necessary to talk about dynamics of any kind now yield to an analytic formalism, simply because you know the functional forms of the probability distributions. What happens if those probability distributions deviate from your assumed functional forms and can take any arbitrary shape or form? What happens then is that the probabilities now cannot be physically realized in our universe, because you're now in a Hilbert space. So your information geometry now lives in a Hilbert space, because you need an infinite number of degrees of freedom to describe this arbitrary probability distribution. So in the space of paths, or probability distributions over paths, the sufficient statistics, to use your words, now live in a Hilbert space. So you have to make a commitment to a particular functional form before you can actually write down the dynamics of the system. So what that means is you can acknowledge that variational treatments might be an approximation to the true underlying dynamics, but you cannot say, well, is there anything else that would give me access to those true underlying dynamics? No, there isn't. It cannot be physically realized, either in consciousness or mathematically. It's intractable. And that means it can't physically be realized. Not in terms of assuming that my internal states have information about external states. So, and even if it could, well, because it can't be realized, you're never going to be able to measure or quantify the divergence between the approximate posterior and the true posterior. If you could, you wouldn't need Feynman. You wouldn't need the Feynman variational principle. You wouldn't need variational Bayes. So you can't ever estimate the gap or the band implicit in the Feynman-Jensen inequality. But that becomes, if you like, I think, more foundationally important when you say that not only can you measure how your sense making or your belief updating or your measurement, let's pretend we're James, you can, when you measure something, you never know whether your measurement is a true reflection of the observed thing that you are measuring when you observe something. Can you measure how much you are off? No. That's the whole point. You've only got the measurement. You've only got the products of observation. That's the world in which you live. It's a world of inference. It's a world of probabilities. And that world, the maths of that world is variational calculus. It boils down to the fundamental lemma of variational calculus. It's just getting the right objective functions, information theoretic objective functions that underwrite the measurement. I'm being very polemic here, but you did ask me, and this has been recorded, so I'm giving you a very clear answer. Well, perhaps to a question you didn't ask, but I'm often asked, is anything better than variational Bayes? No.
Yeah, no, thank you. It was interesting. Yeah, no, it's all really interesting. So thank you.
I should just qualify that last thing. So then people say, well, what about sampling? What about MCMC? What about Metropolis Hastings? No, that's just assuming a particular piecewise approximation to the true posterior using a sample distribution, and there are now as many sufficient statistics as there are samples. It doesn't get you anywhere. So I'm subsuming under variational procedures, things like Metropolis Hastings and Gibbs sampling and the like. So that was a nice bit of polemic. Anyway, coming back to the practical thing. So what I think would be interesting for you to meet as a challenge is to provide a numerical simulation or study that speaks to the thing you're trying to demonstrate, which is basically self-organization is a lawful property of the constrained MaxCal principle and or the free energy principle that can be described as expressing emergent dynamics and properties and processes that make a lot of sense in relation to other things, such as predictive coding, such as the thermodynamics of prediction, such as IIT, such as self-organized criticality, such as, and so on. So all the things you had on your screen, they're all different takes on the same underlying process. You chose, interestingly, to make your life simple, something that was producing its own outside, its own data. So it would be really simple just to build two Ising networks and then just couple them. And if you're right, they will learn each other and they will infer each other. And if you're right, they will minimize they will show a slow gradient descent and a fast one, depending upon how you separate your temporal scales and the parameters from the states and the like. But whatever will happen is that as they self-organize to a variational free energy minimum or a path integral of such, then they will start to learn each other, and they will evince something called generalized synchrony or synchronization of chaos. And in that, you will also get for free self-organized criticality. And if you can demonstrate that numerically by just coupling together two arbitrary Ising networks with a bit of structuring, if they're too homogeneous, it'll be a trivial solution. They'll just collapse onto an identical synchronization manifold. But if they're interestingly structured and slightly different, then they can learn from each other, then they will ultimately converge on something called the synchronization manifold. That synchronization manifold just is the statistical manifold we were talking about before, whose rules include the fact that on the synchronization manifold, there is a free energy functional that has a curvature, that determines the Jacobian, that determines the eigenvalues, that determines the likelihood of exponents, that determines the local linear stability, that determines the self-organized criticality. So all of this, I think, could be really nicely demonstrated, not by one Ising system talking to itself, but by two nearly identical Ising systems talking to each other, and then look at the emergence of self-organization. And then you can tell a story and talk to dynamical systems theorists about synchronization of chaos and self-organized criticality using the language they would understand, but you've generated it from the first principles of self-organization and information theory. That would be in continuous state spaces. This is an example of that kind of paper, which I won't go through now, but I'm just putting this here as an example of using a continuous state space set of two pairs. Well, in fact, it was literally two pairs. A pair of continuous state space neural networks that teach each other, where the dynamics of both are descents on the gradients, the variational free energy gradients, or the Lagrangians gradients supplied by the other one. So again, quintessentially relational. It's not relating to myself. It's it's not. It's self-organization with of an open sort where there is another in play. It just so happens that the other is identical to the self in this instance, and you get this sort of this generalized synchrony. And I repeat, this used continuous dynamics and continuous gradient flows. And simulated bird song. So the two systems here were treated as basically birds singing to each other. And then you can sort of illustrate the synchronization manifolds that come out of that and relate it to dynamical systems theory. So, but that would not be so easy to do with a sort of bitwise Ising or sort of Potts spin glass model. There are examples using spin glass models, but I think the simplest way, again, this is not particularly relevant to the paper. I'm just putting this up because exactly as you've noted and as sort of alluded to by Dalton, you can discretize things in the spirit of quantum mechanics, for example, and quantum information theory by moving to a discrete state space model. It's not quite the same as an Ising model because it's not that all your states are on and off, but they have a probability of being on and off. And as soon as you have a probability of being on and off, you've now got a statistical manifold. You've got an information geometry, which is actually a simplex. It's a very simple information geometry. And equipped with that, you can now rehearse all your maths. And the ultimate objective function in this particular paper was exactly the mutual information that we started talking about at the end of the day, it's just a constraint mutual information. So this is the ultimate objective function that you'll find throughout machine learning when applied at the appropriate scale. And it is, I repeat, it does, if you like, this parody or reflect constrained maximum caliber, but now read in a slightly more nuanced way because you've got these explicit partitions of different kinds of states and parameters now as a constrained maximum mutual information. And which of course includes the maximum entropy, but you're equipping it with a relational aspect. So it's now maximizing a KL divergence or a mutual information or an information gain. And the constraints here are specified again by the generative model, but in this instance, it's discrete state space just as a categorical distribution over all the different states that could be occupied. So it's this which gives its structure. But otherwise, it's just trying to maximize the mutual information. So you could look at this in a very loose way as, if you like, a generalization of MaxCal to discrete state spaces that accommodates now. It's not just the entropy, thank you. It's the mutual information that you want to maximize between the states that are measuring and are observing and the states that are measured or observed.
Thank
and that's
you.
it. Yeah, that's
yeah, I think that's interesting, if I may say, just because I did a couple of simulations on simple networks, and they did appear to learn each other. Something quite interesting is that even when the loss didn't go to zero, the VFE did, and the difference between the VFE and the loss is specifically the pairwise mutual, in this case, entropy rate, but it's essentially related to mutual information. And so
good.
I'd be really interested to investigate that and also try out the experiment that you suggested.
Yeah, well, it's good. Yes, thank you for mentioning that. Yeah, so that TMP, that transition probability matrix, that in that last paper, that's is exactly that kind of structure. You try and maximize, you learn, but you only sort of change the weights, as it were, or change that TMP when you increase the mutual information. And of course, because it's a TMP, a transition probability matrix, you're now talking about the transfer entropy from state T to T plus 1. So, but the same rules apply. You're just trying to maximize the mutual information, which of course in the limit will mean that every column of the probability transition matrix or transmission probability matrix will be occupied by 1 somewhere and zeros everywhere else, and the rows will only have 1. So it'll be a permutation of an identity mapping. You can't get a better mutual information like that. And of course, that is an Ising model. It's just basically switching from one state to another one. So in the limit, when you've minimized your free energy, you're back to an Ising model.
Thank you. Thank you so much for all of your feedback. It's really, really helpful. And I really appreciate your time, as well as everyone who attended as well, the committee. Thank you so much.
Thank you, Alex. Thank you, Carl. We'll finish with one more round of applause for Alex's presentation. Okay, thank you everyone for coming. We will upload that recording, Alex, and send it to you directly if you like. Okay, have a great rest of the day, everyone. Thanks very much.
Thank you.
Thank you.
Bye-bye.